So let's see. Developer make library बनानी है. Let's say test. Okay. And the most important thing is attach an existing technology library where we will provide our technology, suppose UMC or TSMC. So let's say you're writing on UMC. So here is our library. Then we need to create a cell view. You can create a cell view for let's say or here. So here we have a cell view and a schematic file, a blank schematic file. So let's see how we will make them or make them. First thing we need to select the library for our transistors, that is UMC 65 and cell we want NMOS N12 LVT, low threshold voltage, low leakage, and you can place one here and we need one PMOS. We have our PMOS. Now we will be making this gate in our CMOS configuration. So this is what it looks like. So we need OR gates. So copy this one and it here. Yeah. And better we first find these answers. So suppose we want 400 nanometer. 400 nanometer. And this one we want 300 nanometer. Okay, then we can copy this. So whenever one of our inputs is 1, we should get a 1 out. But in CMOS configuration, we don't get 1, we get 0. Why is that so? We can make either way, but this is better for performance. So once we make this, so this will go in series. Once we make this configuration, suppose I give VDD here. Suppose I give so let's see what will happen when we take our output. Like that. And we have our two input A0, or let's say so when either one of them is 1, so one of these answers will be conducting So we will get a 0. So, okay, the logic is reversed. But if we get 1 and 0 and 0, so both of these transistors will conduct and we will get a 1. So you can see the logic is reversed. Therefore, we need an inverter here. How do we make an inverter? One CMOS inverter is PMOS and NMOS. Is that inverter? We can connect this into VDD and ground. Both of these plates will be connected together and Y bar. क्या कर रहे हैं सर? ट्यूटोरियल बना रहा हूँ लोगों के लिए ट्यूटोरियल लेआउट ट्यूटोरियल सिखा रहा है यस किसको जिसको भी सीखना हो यूट्यूब पे नहीं रिकॉर्ड कर रहा था मैं तुम लोग देख लेना बेसिक्स ऊपर डन वही पर देख लेते हैं अब हमारा यहाँ पे वी विल गेट आउटपुट जो है ये हो गया वाई Now in CMOS configuration जब हम ये गेट बनाते हैं और गेट it actually turns out to be a NOR gate. So that's why we need this one inverter to again make it OR. It does require more transistors, but it performs better in terms of noise margin and power consumption. Not in power consumption, I think, but noise margin and stability. So let's verify the functionality. If we get 0, 0, these two transistors will turn on and we will get a 1 inverted, then we get a 0. If we get 0, 1 or 1, 0, uh, this path is not open, but one of these paths is open. So at 0, 1 or 1, 0, we will get a 0. Inverted, we will get a 1. And when both of these are 1, again these are off and these both are on, then we will get 0. Inverted, we will get a 1. So our OR functionality checks out. Okay, we will first. One thing we need to do is we need to connect these bodies of NMOS and PMOS. NMOS body will go to ground. All of NMOS body. This will also go to ground. Okay, we can also connect this separately. And this also needs to go to ground. This one ground. So it is also connected. It's not a work. And this one will go to VDD. This one will also go to VDD. And yeah, this one will go to VDD. This is P1. This will go to VDD. And mass ground. Then last thing we need to do is to place pins. We press P and you can just give our things VDD, GND, N1, N2, and Y. VDD, GND, N2, and Y. Here you can just place wires here, and because we are connecting these wires to the pins, these wires would automatically be labeled according to the pin. So we have just created a net using, suppose we have connected a wire to this pin Y. Once you can check that the bottom left corner, it is showing net Y. So it has, this net has been named Y. So this net is also named, it's basically we have got it. And here you have all our net. You can now do it, not here. Okay, save. It is done. Here now we can do two layer. Then was launch Excel. View automatic. This will remain same. As pressing down, 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 Also, you need to test the functionality using ADL. Yes, from ADL. The pins you created, VDD, GND, in one you give inputs using the actually since Y is our output, then you can change this to output because we are not doing an input to it. Um, Plus VDD and GND, we can go for input output both. I don't think that makes sense. No errors. You can open ADL. This is it defines stimulus. Stimulus is the input that you have this way. Stimulus. First, we need to enable this thing from here. Define kind of activate your phones and then define the voltage. You can give 1.2 volts of pulse delayed by 10 nanosecond. Pulse of 10, this is 20. Okay, you can define all of it. So, GND would be DC voltage. GND is 0, VDD would be 1.2 or whatever rating would be. Then make sure to enable this. I, yeah, I'm not doing it, but another important thing is you need to actually add a test. So we need to test the terminal again and then conclusion. The test has been added. We define input, we have defined test, and now we need to define output. What all we want to see in output waveforms. You can even see the input waveforms as outputs. One, two. I want to see two inputs and one output. We have press escape. So these three outputs are defined. When I run it, it will show me the answer of this. Yeah, you can check the you have about simulation. Then we'll come to layout. And here we open this layout. So first thing we need to do is set the snap. It is better to work at a smaller snap and suppose our 0 point usually 0.5 or 0.05 works good. So yeah, the smaller you make it, the more difficult it will be because cursor would travel to multiple states. But that's using 0.05 snapping would be better, easier. Yeah. Then we will start with connectivity, generate all plug source, press enter as it is, delete this useless thing, press shift and F to view these transfers if they are in symbol form. Shift plus F. Okay. If you zoom in, it will also have created some codes. Delete them. उसके बाद identify the transfers. This is PM0, this is PM1. So these are two PMOS connected in series. This is NM0, NM1. So these are bottom transistors connected in parallel. And these are two transistors are inverted. So we can just do it then for now. Yeah. Now this is the main thing. We need to avoid these two transistors because we can place them far apart. So you can change this setting to freely move an object around. It is not always preferred because when you are making a symmetric design to copy elements from one block to next. So it's better to keep this alignment in perpendicular so you don't accidentally shift up and down and drag in one direction. But if you want to make it more speedy, you can do this and इधर आ गया. Yeah, it's better to rely on align, which will come out by pressing A. When I press A, the cursor changes and we are now into align mode. Yeah, this is PM0. You can see in the bottom left corner what instance it is. PM0, PM1. Check our layout. PM, it's PM0. Source is going to VDD. Its drain is going to the source of other PMOS. So drain of this is going to source of other. Here we can do like this. We can just press E and create a wire. Click once to bend it, click once to bend it, and double click to end. Yeah, that's sad wire, but whatever. Okay, we can do like this, but it will waste a lot of area, and this is just not not a good method. Okay, what we can do is we can press A, click on this edge. It will show this dot. Click on this edge. So the first object will shift. Whatever the first object you will click will shift towards the second object. So where we want to shift it, not here. We can also do like this. This will also work. We can just create a connection from here. Yeah, or we can just create M1 a rectangle of, let's say, M1. We can also do like, see, I want to snap on this, but our snapping is too big. I want to precisely start from. So we can just reduce snapping 0.05, 0.05. Yeah, now I can snap to this. I can make a rectangle here because it will connect it. Or I don't want to waste metal. I can make. So these are another important features. DRC enforce, DRC check. They will give real-time information to you about DRC violation. Suppose I am starting a rectangle of M1. So it will tell me that I need a minimum width of 0.09. So I can just start with that length, and rather than going to DRC and mentoring, can increasing the area or thickness. So it will also show area, how much minimum area I want. As soon as I touch to this M1, uh, so minimum area, we can ignore the minimum area if we know that another metal one's there and join it and even added, like it will become one single meter. So in that case, we can just ignore it, otherwise place it like this. Yeah, this is also a valid way, but another better way which we should use is, it was initially here now we use A, align this, and we will align it to this edge. This edge or this edge, I think it will snap to the same thing. Not this one. Snap. Let's try this. It's not happen. Source is coming from here. Drain is connected to source. There is no contact because it is internally connected. We don't need to connect any wire here. Then it is going to the drain. Source, drain. This drain is going to source. Then it's coming out of drain, which is connected to output. Yeah, next. Yeah, so source, then it is going to drain, then drain to source, then source to drain. Yeah, you can confirm whether these transfers have been aborted successfully by going here. It will tell you instance P1 aborted to instance PM0. This is very important to confirm that you have successfully aborted them or not. Here, let's see these NMOS. How can we abort these? So, NMOS, both of the sources are connected together since it is in a parallel configuration. These transfers were in series mode. So, both of the sources are connected to ground. They are shorted together and connected to ground. And both of the drains are also shorted together and connected to this net. Yeah. When I generated from source, it oriented the transistors according to the schematic, but sometimes suppose I want to avert C. This is the case. I wanted to avert, I wanted to short both sources and both drain to drain and sources to source. But if I select this and do this, this is drain, and this is source. So I can't just like this. It will it will abort, but it will give LPS errors. Yeah. What we need to do is we need to flip one of the transistors. I can flip this one. Our source is coming from bottom. Yeah, so it's better to keep those outside. Those source drain. Let's see. You can do either way. Let's see. First, I will flip this transistor. So drain are at the same way. You select this. Now I can align them. If I align them, now drain and drain are averted. I can check from here. And then 0 and 2 averted. You can check and see method. And 0 says and then 2. Yeah, now as time for move, select both of these. And if you select one of these, the button will go away. So select both of them. Now here is a major DR step. This is, you can see, turn off all the other layers, turn on N1, and turn on um, N plus region. So N well and N plus region plus. So we have a constraint here about the distance. Minimum distance it needs is 0.2 micron. That's 200 nanometer. So 0.02 micron, 20 nanometer. So no, 0.2. Okay. So this is the minimum distance we need to keep between. So we'll work with the minimum distance to save area. We will shift it around here. Yeah, these borders, these lines are for n plus region, and there's p plus. So basically, it says that p and n region separation. Okay, we got the separation. It's on all the layers. Now you can also use align tool in this way. Suppose I want to align this edge with this edge, that it should start from the same line. So I can, if I want to shift this one, select this and select this, it will be aligned. These two edges will be aligned. And if you want to attach them, you can do this one and push this one and this one. It will come down, or it will give the articulation. Yeah, so it's always better to start your design aligned with each other because then you will place multiple blocks. Suppose multiple OR gates are connected back to back. So if we copy paste, um, copy paste, so it will not create any gaps or discontinuities. You can align your design. Yeah. Awesome. This gap you see above between PMOSs, it can be dealt with. I'll tell you later. So both our PMOS and both our NMOS are now averted. Now we need just to connect the inverter transfer. Mhm. It is what I can what we can do is I don't want to measure this 0.2 micron distance again. So I'll just align this with this and this and this. Yeah, we can align these transitions. There is no problem. These are not about it, just align. उसके बाद we can align this and MOS with this. Okay. Otherwise, also if we want some separation, we can first align and then move this one. Select this option, go to perpendicular. Okay. Then you can shift it here and then also shift it here for any case if we need gap between. But our distance is maintained. It is aligned with this. So it is better to make your design as symmetric as, because when you do hierarchy and when your design gets bigger, then it will be very much rewarding to have a symmetric design. You will see later. Okay, we can work with this. So our transfer placement is done. So as soon as our transfer placement is done, first we will do our PRC before making any connection. Because we need to make sure that however way we have with the transfer is correct or not, or spending any time on wires. Suppose now I place wires here and then I go to DRC, then it says that no, this transfer needs to have this equation. I will move the transfer, then I need to go first make a placement, then to DRC, then go. So the same bottom and DRC. First, you will select the whole file and play. According to your technology, whatever file you have installed. उसके बाद to inputs, make sure this is checked, export from layout viewer. This will export this layout, generate next from this layout and export it into this one. Check this name or the cell view name is or this checks out. Of course, we don't do anything. It is saying that my layout has been altered, not because I did not check and get when this right here. Review recording. Poly area, it is saying that the area of poly layer is not enough. We can't do anything about it right now because we have not made any connections. When you connect these gates together, see these gates are connected now. This PMOS gate and this NMOS gate is connected. This PMOS, this NMOS gate is connected. These two gates are connected. When we connect this, poly density we could at the smallest level. When our design gets big and interconnected, even this density around will grow. Let's see what this is saying. Minimum space between two and plus region is 0.18. Let's see. If we double click on it, it will highlight there is a problem. We can turn off all the layers and plus layer is on. Suppose initially we have this. Okay. So it is giving error about n plus region. So I'll check at the n plus layer. Now if I delete the highlight, you can remove the highlight from here. So you can see that there is a gap. Now here it is saying that this gap needs to be at least 0.185. If I turn on, okay, let's measure what is this distance. So if you press K, a ruler will open up. You can click on that is 0.12. 0.18. It is saying that I need to move it. Yeah. I can do it this way, but again, this area is being wasted. And what I can do is select this emphasis layer, this path for rectangle, and connect this to just fill the gap. It is saying I need minimum area of 0.18. I can just start from a little bit ahead and overlap these two regions. Yeah, I can ignore minimum area because it is being overlapped with other areas. So basically what I've done is I filled that gap between two regions. Now all of these are at same potential. The ground of all these transistors are connected together. VDD of all these transistors are connected together. So we can connect these two to create a children. Let's check the next DRC. This is about maximum amplification to nearest capacitor. I think we can also ignore it for now. We, yes, let's take this one. So we have the same thing here with P plus even. Minimum spacing and notch of P plus is 0.8. So we can apply that trick here also. Select P plus, create a rectangle, remember its same, pass on here. So, next, I think you can also ignore this one. I think it will go away when we do connection. Let's see. इसके बाद M1 area, it is saying that area is not enough. If you make a patch of M1, it should have a particular minimum area. It will also go away when we make connection. Yeah, this is about density. All density errors we can ignore. Okay, the main thing we check for placement is whether if it is giving any error about n well or n plus regions like I did this and this. Once this is done, save. Now we can do connection. Okay. And now the source of this CMOS was coming from really. First time what I can do is detach the body. Body type is moist and release. Yeah, I got this. This one is enough for all these transfers. And same with this. Now you can choose you want to go detach it upwards or leftwards depending on your design. You want to make a lateral design or a vertical design or a square design. So you can manipulate some of those things. Really much. Oh yeah. Here it is showing ground. It's showing VDD. Now let's start from here. This VDD will go to source of this beam. So let's take more angle, or what I can do is straight up click and connect this. It is connected to VDD. Source of this transfer is connected to VDD. Okay, drain is already connected. Its drain is already connected to source because of drain. Then now drain is going to the drains of NMOSes. So this drain, see, remember this is the transfer of inverter test. Just look at these two transfer. They are so drain. This drain is going to the drain of this NMOS. Alright. So so what we can do is let's try this. Yeah, we'll move it from here. Yeah, also flip this on. Body side or legal. Left. Now align. I need to move with this align. I need to move this one to this one. Averting, averting to the done. Stand guard. I need to move this one to this one. Yeah, now what's the benefit क्या हुआ? I can just सीधा connect wire. Wire will come from P session P. थोड़ा सा bend करना पड़ेगा इसको. और better is you can just and leave it there like this. And yeah, this is our white edge. You need to check that that name is coming automatically. The lowest name. It was white edge. So what you have done is VTT is going to source of PMOS, then the CDs, and then drain. So we have come to the middle. Let's start with this thing, MOS and MOS. There its source is going to ground. We have averted the source, it's the ground, then remove the wire. This wire can overlap this poly, but see another this one is there, and minimum suppression should be 0.0. So I need to eyeball it, I think a little. So I can just hopefully make this to okay, I can use this touch. Move it, contemplation. You can read it is fine. And if you want to be very efficient, just just and make this in so source of you can ignore this that connection is weak, but it's just a one line. And it's going to both of the sources and both of the drains together and connected to the midpoint. So these are both of the drains. Then to the shower connected to this. Keep the wire with like this. So both of the drains are shorted together. Both of the drains are shorted together. Connected to the neck. This is one image. Now let's see about the input. We actually we need to remove this because it's the negative variable. What we can do is we can just create a via. Why do we need a via? Let's go for via from metal 1 to poly. Because our signals are coming on metal 1 and metal 1 is connected to poly. So it is just a through hole in the stack of all the to connect. So the green square in the middle is a control point. So you can connect to this blue here and put this here. It is showing minimum situation for M1. Okay, what we can do is you can press M, move this one little bit ahead. Okay, you can press S to stretch this back here and stretch this one thoda sa आगे. So this area would be considered a single area, so this is connected area. And then now I can copy and this is wherever it allows. I can see how it's already showing in one because this is one this is one PMOS, this is one NMOS. Both of these gates are connected together, and it is I think this one. This is one PMOS, this is one NMOS. Both of these gates are connected together. So, and if we connect this one, it should show in SP wire select E wire then okay. Now I can just shift it little bit upward. Okay. Now the problem is we need to connect this drain to this drain, but we don't have enough metal space. What we can do is move this one without it won't see. So let's see. Now we need to connect this drain to this one. We go upward from here. Now what we can do is either we can take another metal layer here and uncheck use spot and do the drawing. Um, and E tool is smart. Yeah, now we can do connection on any two layer. Press R, do this, or you can make it smaller to save metal. You can place it anywhere. Now there is metal 1 below, metal 2 above, but there is no connection between them. That's why we need a via from metal 2 to metal 1. Place it above the connection. एक इधर हो गया, एक इधर हो गया. ठीक है. सिस्टम इसके बाद लेट्स सी अब ये हमारे दो ट्रांजिस्टर इनका VDD you can take VDD from E transformer से into this resistor connected to this VDD. This this is VDD and इसका source जाएगा ground पे. You can connect it from here. I did this by pressing S for stretch. Now VDD is connected, ground is connected, both of the gates should be connected and both of the drains should be connected. So both of the connecting both drains is easy. Take this one, drop it here, this click, this here, click, done. Then again copy, press C for copy this here, place it here, um, move this one, put this right. Move this above, this poly. Or I can align this and this. The E is connected here, this is connected here, it's doing Y bar. That our Y bar should come at this gate. This Y bar should come at this gate. So where is Y bar? There is Y bar. What I can do is create a rectangle on this one, only one. Angle on only one. Start from here. Whatever minimum area 0.9 is connected to Y. And this is our output Y bar. Make a rectangle here to connect this. Will connect this. This then a last चीज रह गई है to place the pins. Will create L पहले DRC check कर लेते हैं. It will show some DRC I think. Let's see for area of this metal too. This also has some constraints. Hmm. See, we can ignore this poly density. Let's see this one M1 S2 spacing of M1. Somewhere we are violating the space and here it is. Okay, this notch. It is saying that this spacing should be greater than 0.9. But we can just correct this by removing this notch altogether. Just create a rectangle over it. Yeah, now there is no notch, no spacing. This is lifted. And I think this is done. The sum is done. And one area, it is saying somewhere area of M1 is not sufficient here. Yeah, because it is assumed that when we make the next level or copy this device to somewhere else, the connections would come from here and it will add to this and this will go away. But for now, what we can do is create R1 and just select this much area. I think this is just give it a like so from here. Whenever this message goes away, uh, this is running here also. Or we can do one thing, copy this thing and showing area this video I can increase in the download directory. Yeah, that's enough. This is done. I think this is also done. What is this thing? They're all highlights. Highlights. Check this one. Area of area. Anyone. Acha. There is no other anyone here because we connected any two from here. So we need also need to increase the area of anyone here. Area. Wait. So switch it. And some edge created. One thing. And last one is he said after we are aware of it. Now only two errors should remain, this poly density and L2 density. Yes, still not sufficient. We can test this one. Remaining and editing doesn't take much time, but running this ERC, LVS and waiting for them to open this takes time. Awesome. Then running ERC. Hmm. Yet the licenses are not free, but I'm confident that ERC is done. Yeah. Now you can see कितना compact में बन गया ये. There's not much space being wasted. You can measure 1.4 micron, Memphis 2.65 micron. The design looks clean and compact. Stiff bar, also, whenever you are doing DRC or LVS, you- Hmm. So whenever you set up DRC and you close it, it asks to save or unset file. You should save or unset file. Means next time you can just load that unset and directly see. We got the license. Yeah, now I consider this as ERC done because only everything is urgently. So this ERC will come equal to NVS. Second, confident my connections. I can say for sure that LBS will come out to be correct 100%. But with that, we will create things. They will use maybe they wanted to use GND, maybe GND 1, 2, and 5. Select layer. This is important. On which layer we want to do. Select any one CAD, the row number CAD. The bottom there is text. Yeah, um, this, one, two, maybe I will go to replace it anywhere on the net. So also there, sit here, sit here. Usually it will ask if I want to place it on this transfer or this rectangle. Okay. So this is the one rectangle. Then we will go to here and one drawing. Yeah. In one. This is in one, in one rectangle, in two, in one rectangle, and of course y. See, I'm confident I'll be correct. Select LVS. Make sure export from layout view is selected. From netlist it is selected. Export from schematic view. Both the file names are same. Run. Yeah, LVS correct. Done. These are our gate. So that's it.